Hey everybody. Today we're talking about sums, multiples, and means of normally distributed random variables. We are in a situation where we have a collection of independent random variables, each with a normal distribution. Let's call those random variables x1 up to xn. It seems logical that we ought to be able to say something about the distribution of their sum, their average, or constant multiples of them. Here's the big fact telling us how to do that. Suppose we have a couple of independent random variables, x and y, with normal distributions with known means and variances, and suppose c is a constant. Then the distribution of c times x, the constant times x, is going to be normally distributed. The mean will be the constant times the mean of the original normal distribution, and the variance will be the constant squared times the variance of the original distribution. If you take the sum of those two random variables, x and y, that sum is also going to have a normal distribution. The expected values, mu sub x and mu sub y, those add, as do the variances. If you combine these two facts using c equals -1, you can verify directly that x minus y is also going to have a normal distribution. The mean will be the difference of the means. The variance will be the sum of the individual variances. Both of these facts are proved using moment-generating functions. So here's the proof for the distribution of the sum x plus y. We take the moment-generating function of x plus y and we just write that out. We break it up using properties of expected value for independent random variables. Plug in the moment-generating function for the normal distribution. That's what's happening on the middle line there. Apply some rules of exponents, and at the end, we get the moment-generating function of a random variable with distribution, with a normal distribution, with mean mu sub x plus mu sub y, and variance sigma squared sub x plus sigma squared sub y, just like the fact claimed. The proof for c times x runs with exactly the same steps. Okay, let's do an example. A commuter can take two different routes to work. When taking route A, times are normally distributed with mean 25 minutes and standard deviation 4 minutes. When you're taking route B, times are normally distributed with mean 23 minutes and standard deviation 7 minutes. Ultimately, we'd like to find the probability the route B is actually faster on a particular day. So as usual, I recommend pausing the video here, trying this on your own before seeing my solution. As a hint, I would say to consider a new random variable defined to be the difference between the two that you have here. Before I actually solve the problem, I want to show a quick visualization here. Here we're seeing the density curves for the two different distributions corresponding to routes A and B. Route A here is shown in teal, the sort of bluish color, and Route B is shown in orange. You can see that Route B is centered to the left. It has the smaller expected value, but there's a lot of overlap between these two distributions. The difference in the expected values isn't that huge compared to the variability within the two different distributions. So let's let x and y be the times taken on the two routes A and B, respectively. So those have known distributions. And let's consider the difference. Let's call that a random variable w, defined to be y minus x. Using fact 1 from a minute ago, we know the distribution of w. It's going to be normally distributed with mean -2 and variance 65. So of course I got that just by subtracting the means and adding the variances. On average, route B is going to be 2 minutes faster, though since the standard deviation is nearly 8 minutes, there's a lot of uncertainty involved. Here's a quick plot of the random variable w's density curve, as well as a visual representation of the probability in question. We're going to be interested in the probability the route B is faster. That corresponds to the probability that w is less than 0. And you can see from this plot it's going to be a little bit more than 50%. This is a normal distribution centered a little bit to the left of 0, so the probability of randomly getting a value less than 0 should be more than 50%. We can actually compute this using technology. I'm going to use R as usual, where the command that we need to use is pnorm. To get the probability of a random value less than 0 in this distribution, we do p-norm of 0, comma, -2, the mean, comma, square root of 65, the standard deviation. When we carry that out, we get about 59.8%. Now let's consider the average of a bunch of independent, normally distributed random variables. Here we're going to assume that they all have the same mean, mu, and the same variance, sigma squared. Although if that's not the case, you can still do similar operations as we saw in fact 1. The result is that sample mean x bar is going to also have a normal distribution. Its sampling distribution will be normal, with mean mu the same as the original variables, and variance sigma squared over n. So there's less uncertainty involved in a sample mean as opposed to individual observations. The proof of those two facts for the mean and for the variance just uses fact 1. Here I've written things out kind of longhand so you can see the individual steps. Fundamentally, I'm just using properties of expected value and variance. For instance, let's just talk about variance for a second. The variance of x bar is going to be the variance of 1 over n times that sum. Using properties of variance, the 1 over n gets factored out as a 1 over n squared. And then the variance of a sum is the sum of the individual variances, all of which are equal to sigma squared. So far we have 1 over n squared times the sum of sigma squared. That sum is just adding up the same thing n times, so that sum is n times sigma squared. Now we have a factor of n in the numerator and a factor of n squared in the denominator. There's cancellation, so the variance of x bar is 1 over n times sigma squared, as claimed. Let's wrap up by doing one more example. When properly calibrated, a machine fills soda bottles according to a normal distribution with mean 12.10 ounces and standard deviation 0.07 ounces. What's the probability that an individual bottle is underfilled? What's the probability that 10 bottles have an average fill of less than 12 ounces? So here we're in a situation where, maybe the bottle is labeled as containing 12 ounces, and we're concerned about whether the consumer is actually getting what they're paying for. So if x represents the fill of a single bottle, we know its distribution. It's going to have a normal distribution with mean 12.10 and standard deviation 0.07. And so we can compute the probability that an individual observation is less than 12 just with another p-norm. P-norm of 12.0, comma 12.1, comma 0.07. And the output of that is 0.077, about 8%. So even when the machine is properly calibrated, about 8% of the time, the consumer is getting shorted. If we're going to talk about 10 values, 10 bottles, we are going to view that as a random sample. So we're going to assume the observations are all independent of one another and that they're coming from this normal distribution with mean 12.10 and standard deviation 0.07. According to this last fact number 2, x bar, the sample mean, has a normal distribution with mean 12.10 and variance 0.07 squared divided by 10. So the standard deviation will be 0.07 divided by the square root of 10. So we can do the probability calculation x bar less than 12 using almost an identical p-norm. The value of interest is still 12. The center of the distribution, the mean, is still 12.0, but now the standard deviation is smaller. It's the square root of 0.00049. When we do out that arithmetic, when we enter that p-norm command into R, we get 0.000003. So the probability of getting 10 bottles whose average fill is under the target value of 12 ounces is extremely small.